run it, you type macro pp space file name, and without the print macro call inside your main method, it would output the case to disk, but it wouldn't show me the macros that you have yanked out. So I wanted you to send that to screen. So the print macros prints to screen. This is what you're taking out of the source code file. Then you send the disk to screen as it's modified. So you're going to do two things, output to screen and also to disk. Now then, what is outputted to disk is not critical at this juncture, but I want you to go ahead and get that in place. What you're going to have to do is comment out the macro invocations and do the expansions. However, that's the next project. That's project 3. So if you just let it pass through with the macro definitions taken out, that will be fine. Does everybody understand what you're supposed to do? Okay. Formatted output. So you're going to need to format your output in some fashion, and there's an easy way to do this. It is with set the width method. So you might have something that looks like this. Just a general format is cout. And then whatever the variable is. And so on. So this will give you exactly 10 characters for each field, and the columns will line up. The tab characters don't work very well, as you probably know. They don't line up correctly, but this way each column has exactly 10 wide. So that may help you when it's time to output your data or your file. Okay, are there questions about the assignment, anyone? Really? Okay, cool. So what do macros do? What's the function of a macro in a program?
To do lots of steps.
Okay. Do steps? What kind of steps? All right, let me suggest this. Yeah, Kenny.
I was thinking it's do like one or two like commands and it does multiple things.
Okay, that's true. Yeah?
Is it similar to a method or a function?
It's very similar to a method or a function, yes. But it isn't a method or a function. Well, what happens if I call a method? You go to the method, you do a certain amount of work, and then you come back. All right, so that call stands for a number of steps. Well, a macro, what it does is where you have a single macro invocation, it performs a set of steps that replace that line of code. So if you have the source here, and you have a macro invocation of some sort, macro name, and then the parameters that might go with it. That's one line of code in the source. So then the macro processor takes over and it will comment out this macro name, params because this is not machine instruction, it's not machine code. The CPU doesn't know how to do that. And then in its place, it will insert a set of instructions to do the desired action. You have replaceable parameters. And so they're performed by exact literal substitution, i.e. whatever that parameter is, it is inserted into the source code, exactly as is. Macro preprocessors typically don't do any kind of analysis of the code they're processing. And so for that reason, they're more or less language or platform independent. They're more or less independent because they don't actually look at the source code or analyze it in any way. So if this is an assembler, of course, it has to look up the opcode. It has to decide how to encode the memory reference and so on. So each object or each token has to be looked up, analyzed, processed in some fashion with an assembler. But a macro preprocessor doesn't do that. Does a macro preprocessor catch an invalid opcode? No, it doesn't. Because it doesn't know what the valid opcodes are. It has no concept of that. Well, what is the difference? Well, let's start this way. How is it like a subroutine call? How is it like a subroutine call?
Set of instructions.
It is. So imagine that I have a macro that I'm going to say process line. This is not a subroutine call, rather it's a macro. And then I'm going to say line, the first line. Okay, a function call might be process line 0. So could I construct a macro and a method that would do the same thing? I'm processing a line into tokens and storing it somewhere. Could I write both a macro and a method that would do the same thing? Do I have that choice? Well, would both work? All right, is there any time, can you think of a situation where the macro would not work, but a subroutine would? I mean, are these completely interchangeable or aren't they? Yes?
Like, would the subroutine work for more generic, like input? Macro has to be very specific.
Not exactly. Not exactly. Question? I mean, do you all get the question here? All right. So earlier in the semester, we looked at a method called swap. We were learning C++, and I looked at this. So we have swap int and A, int and B. Can I write that as a macro? Can I write a swap macro instead? So with this language, we would have an A and B, and it might take that form. Would it work the same way? Would it do the same thing? Questions? Do you understand? What do you guys think? Are they interchangeable here?
You're just changing the value.
They do change the value. You're passing in the reference to it.
macros now access the heap.
It doesn't. Very good point. Very good point. Would this work? Yes. You know, you can do this if you write it in the H file. It becomes inline. That's what a macro is. That's what a macro is. So one of the instructions here, well, with swap, you have something like int temp equals A equals B equals temp, and you're out of there. Okay. I could also write a macro to do this. And if I write a macro to do this, then I'm running along in my code here, and I have int x equals 2 and y equals 4, swap x and y. Okay, so that's the subroutine. Can I do a macro? Can I do a macro? Swap macro. Okay, help me write this. So we'll go ahead and use C++, but we'll use the conventions for this macro preprocessor. Int temp equals what? \1. \1 equals \2. \2 equals temp and temp. Questions about this? So if I ask you to do this on a test, you could, right? I mean, your parameters are \1, \2, \3, and so on. Okay. So if we call the subroutine swap, then we leave this place, we jump out, and we go over here, we execute these instructions, and then we go back to the line following this and continue on our merry way. That's how subroutines or methods work. What happens, however, if swap is a macro and I say swap x and y? Now what happens?
Replaces the code.
Yes. This is commented out, and in its place we have inserted int temp is equal to x. X is equal to y. Y is equal to temp. Comment end of expansion. Okay, did we jump out and go anywhere? No, we didn't. We just kept going, marching right down line after line. There's no jump to subroutine. We comment out the macro call, because guess what? There is no C++ instruction swap. The compiler doesn't know what a swap is. Okay, we could call swap if we have a defined subroutine, but we could write a macro as well, and it would take this form. So the difference is, with the subroutine, you jump out, go to a different place in memory, execute the code there, and then you come back. With the subroutine call, where do the parameters come from?
Stack.
The stack. They're on the system stack. You don't use the system stack with macros, so that's off the table. And in fact, with macros, you don't jump out and go anywhere. So would these have the same effect? Is there any meaningful difference between these two approaches for the swap problem? True or false? The macro and the subroutine call have exactly the same effect. One isn't different from the other in terms of the outcome. True or false? What's the difference? Yes?
Does that swap only apply to that one instance, but if you do it again, it'll remain as it was before?
No, you could call it multiple times. Now, I understand you've got int temp defined there, and so I did this to avoid writing assembly language code on the board and confusing something besides the macros. That's what I'm aiming at. That is handled by the \@ thing where you might have duplicates. But you could call this repeatedly. You could call this as many times as you needed to. So you have one line of code in the original, but the expanded file has 1, 2, 3, 4, 5 lines. So one line is replaced by 5, but you don't jump out and go anywhere. So my question is, do these do precisely exactly the same thing, no difference? Yes, they do. Absolutely they do. They have exactly the same effect. X and Y are swapped. Now there are some differences here that I want to talk about. I want to understand, if you're writing code to do something and you don't really understand what it's actually doing, that's a tough row to hoe. I want you to get a good grasp of this. There are differences, so hopefully when we get done today, you understand a subroutine can do this, which is something that a macro can't do, but where are they the same, where are they different? So, okay, when I call a subroutine, I have to use the system stack. And on the system stack, we have a stack frame or an activation record. So each call to a subroutine causes a stack frame to be placed on the system stack. So imagine that you have a Java program you're running. And the first thing that happens is main, because guess what? Main's a method and it uses the system stack. All right, now inside of main, maybe you call read file. We'll just make stuff up here. Okay, so that's a method. Read file is a method. But have you finished main? No, main is still in play, but you've jumped from main into read file. Yes? Okay. And in read file, maybe you call a method called get a line. Did you finish read file? No, you're on one particular line. And then here, inside of get line, you say tokenize line. So, okay, we've got 4 methods that are in play. 4 that are started, none that are finished. They're all in play. Could this happen with a macro?
No.
Well, could I insert all of the instructions for tokenizing a line inside of get line? I could. I actually could. So the stack is not in play here. There aren't subroutine calls, rather the file gets bigger and bigger and bigger and bigger. So what we have here is main. And you jump out of main and you call read file. Can't write. So you jump out of read file and you call get a line. And inside get line you jump out and you call tokenize line. All right, so that's what this looks like. You've got 4 things in play. None of them are finished, all of them are started. Well, What the stack allows you to do is keep track of where you are, but if you're not jumping and coming back, does it matter? So could I have main here? And inside of main, I have a call to read file. So I comment out read file, and in its place I put a bunch of lines, including get line. And then I have end of expansion. Okay, well, get line's a macro. Could I comment it out? I could. So I've got read file, bunch of lines, and now I have get line, commented out, bunch of lines, end macro, but I'm still in this macro, end macro. This one is get line. This one is read file. Can I do that? Yes, I can. So we could keep going here. So could we actually do this thing with macros? We could. All right. So the difference then, I mean here, this is essentially, this expansion is just dropped in, right? It's just, this is replaced by this. Okay, so what goes in a stack frame? The stack frame. So I want general, we need not be absolutely specific, but I'd like a list of the things. So let's say stack activation, or stack frame. Each stack frame, and this is one stack frame, so here's 4 stack frames. Okay, I'll give you something. All of them have a return address. When you get done with tokenized line, you need to go back to get line, and you need to go back to where you came from. That is to say, when you finish tokenizing the line, you need to go back to the line following the place you left in get line. And the way this is done is by saving the return address. So when you jump, the stack has the address to jump back to return to. So we always have the return address. Well, do we have this with macros? No, we don't. Why don't we? Because we don't jump anywhere, so there's no return address to go back to. What else goes in an activation record?
Parameters.
Parameters? Absolutely. Okay. What else?
You need to know where you're jumping to? Destination?
No, that didn't go on the stack. You need to go where to jump back from. The mechanism is this. If you call swap, then a simple table is checked and there's an address or a location for swap. You put that in the program counter, you jump there, and then you manipulate the stack and carry on. Okay. So where you're jumping to isn't there, but some other things are.
Return value.
No, return values aren't placed on the stack usually. What else? Local variables. What else? So this is low-level stuff, right? Think low-level stuff. Saved state. Whoa, what's saved state? Robert, what's saved state? You got this look on your face like I know exactly where he's going. I'm picking on you. You don't have to answer that.
I got an idea. It's like you load everything up on the stack. So you load up the state of where the
instruction was in the stack?
Well, actually not, because the return address is where you need to go back to. To save state though, here's the thing. So imagine that you have a machine that has 16 registers, but you have 100 people using the machine. All right, how do you spread those 16 registers among 100 people? You can't, it's hopeless. You can't. In fact, when you enter a subroutine, you ought to be able to have access to all of the registers with no limitations. Each code segment should be able to use all of the registers that that machine has. And in fact, you can. Well, how does this work? By saving state. So, okay, a simple case here. If you're going to swap two values, then you need two addresses. You're going to have to probably put those in registers. All right, well, what if those registers are in use? What can you do? In fact, you don't know what the other guy might be doing and what he might be using. And so when you go and save something in a register, oh my gosh, you could step on something. So there's an analogy I like to use. It's kind of simple, simplistic, and I hope you'll forgive me for that, but it makes the point. I think it's easy to understand. So, okay, registers hold things. We need to hold things in registers, addresses, for instance, for the swap. So I go over to my buddy's house, and he's got a great big basket sitting there, and he's got his laundry in it. And I say, that's a great basket. I'd like to borrow that. Would you mind if I borrow that? I got some stuff I need to carry. And he says, sure, you can borrow my basket, but don't mess up my laundry. So I say, okay, and I take the basket, and it's got the laundry in it. I put it in my car, and I drive home. Now I take this laundry very, very carefully out of that basket, and I set it on the kitchen table, and I make sure that I don't mess it up. It's exactly the way it was. Now I have an empty basket. I carry my stuff, do what I'm going to do. I get all done. I go back to the kitchen table. I take his clothes, and I set them neatly in the basket. And I go back to his house, and I say, thank you for letting me borrow your basket. And he said, I thought you were going to use my basket. And I said, I did. He said, but it looks like just like I left it. That's the idea. All right, primitive, right? But you get the idea. What you have to do is take the stuff that's in the registers and you park it, not on the kitchen table, but on the system stack. The values that the other guy had, they're not your values. You don't even know if there is anything there. But if you're going to use the registers, then you save whatever was in them, and who knows what that is. You don't even look at it. But you take it, you put it on the stack for safekeeping. And then before you return from the subroutine, you take those values off the stack and put them back in the registers. And this is how you share a finite resource. So if we have a machine like Eterus, which maybe has, I don't know how many registers, 32, and we have 200 people using it, it still works. So we can't share memory that way. That doesn't work. It's too slow. But registers we can and we do, because it's a very finite resource that we have to be able to share. And this swapping around, in fact, happens thousands of times per second. When you switch context between users, the same thing happens. You have to save state. So saved state means things like the registers, the status, the CCR, the condition code registers. All those things get saved on the stack. Then you go do your thing and then you come back. So what are the implications then? What are the implications then if you're not using the system stack? Well, for one thing, macros are faster. If you jump, well, before you jump, you have to do some work. You jump, you have more work to do. You have to manage the stack activation record. You have to save those registers. And to jump from one place to another in memory costs you something because you taint the caches in the CPU. Whereas with macros, you just go down the line one after the other, which is as fast as it can be. Okay? So macros are faster, hands down, period, end of discussion. A lot has been done to optimize subroutines because we do it all the time. And we wouldn't even think of writing code without methods. That would be crazy. But understand there's a performance cost associated with jumping. So the swap method here, we've got 3 lines of code. But how many instructions might this execute to do the swap? I mean, what's the overhead associated? What would it cost? So to manage the stack, to do the jump, to restore the state, you may easily do 1,000 things to do that swap call. So if you have a macro, how many things do you do? 3. Yes. Now computers are really fast, and as I said, they're optimized to handle the stack this way. So you don't want to get the idea that you've got to stop writing methods. Don't do that. But at this low level where we're looking now, the reality is macros are faster and more efficient. Okay. So if they work the same way and they're faster and more efficient, then why do we write methods at all? Well, what can a method do that we can't do with a macro? Well, there's one biggie that jumps out here. Recursion. Recursion. Now there's kind of a subtle reason for this. Can you have a macro expansion inside a macro? Yes, well could you expand the same macro inside there? Could I do get line instead inside a get line if those are macros? I actually could, but there are problems with it. Macro expansion happens when? Well, there are 2 big ideas here that it's important to understand the distinction between them. And that is assembly time or compile time versus runtime. All right, so recursion happens at runtime, but macro expansion happens at assembly time. Okay, well the recursion has to be a runtime thing. So it isn't going to work for that reason. There's another reason. Suppose I do a simple recursive method. Let me think of something trivial here. Triangle. Yeah, n equals 0, return 0, return n plus triangle n minus 1. All right, so what this is a recursive method of calculating the first n integers. So if I say call triangle of 4, we don't need a great big one. What happens? Is it 0? No, okay. It's 4. So this is 4 plus triangle of 3. Okay, calls triangle. What's triangle of 3? Well, it's not 0, so it's 3 plus triangle of 2. And actually, we could change this to 1 to make it simpler. There's no reason to go that extra time. Same thing. This is triangle of 2, so we jump out and we do triangle of 2, which is 2 plus triangle of 1. Okay. So now we call triangle of 1, we have 1 plus triangle of, well, that's where we return. Here we come back because it's 1. So the return value here is 1. So we return 2 plus 1 is 3. So this replaces this call with 3. So we've got 1 plus 3 plus 6. 3 plus 3 is 6 plus 4 plus 6.
10.
What's this one?
10.
Okay, so that calculates the first n integers. All right, so can we replace this with macros? No, why not? Well, how many values of n are there here? At runtime, when this goes, how many values of n are there? There's 1, 2, 3, 4 values for n. Are they all in? Yes, they're all in. Okay, how does this work? The stack. The first time you call this, n is 4. And then you call it, n is 3, n is 2, and finally n is 1. Okay, so you're done with this. You return 1 is popped off the stack, and the top of the stack is your n. N is now 2. So you add it to the return value and you have 3. That's the return value. This is popped off. So the return value, 3 plus the return value is 6. Everybody with me? So this is popped off. Well, now n is 4. 4 plus the return value is 10. Okay, we had 4 different n's. But with the macro, we can't do that. We don't have 4 different n's. So recursion's out of the question. Any kind of recursive call, the recursion that happens at assembly time is quite different. Part of the problem, too, is I don't know how in the world you would ever get a stopping condition with that. Can you call a macro inside a macro? Yes, you absolutely can. But recursively, not so much. So there are 2 requirements for a recursive algorithm. There may be other things, but 2 big ones jump out. 1, there must be a well-defined stopping condition. Because if inside of a recursive call, you have a recursive call, how does it stop? Where does it quit? And under what conditions? So what happens if I do this? If you type that up in a Java program and run it, what happens? You call foo 1 time, right? So in my program I say foo. Now what happens? You blow off the end of the stack. Yes, you exhaust the stack and run off the end, and then you crash. Why? Because there's no well-defined stopping condition that you can always reach. Okay, how could you create a macro where you have a well-defined stopping condition? You couldn't, right? And that is corollary to the other property here, which is each invocation, each separate call to the macro or subroutine must represent a smaller set of the problem, a smaller version of the problem. That is to say, you need to be able to demonstrate that you're making progress. All right, so with a macro with just substitution of instructions, the problem can't get smaller. But the problem needs to get smaller or you never get done. So recursion is out the window, won't work. So there may be other issues where the stack needs to be used and can't be with macros, but pretty much many of the subroutines you do could be replaced by macros. All right. So what data structures do you need? How do you need to store information? Hey, let's talk nuts and bolts. what has to happen here for your program to function correctly?